Welcome to the Foundry by Forge College. Okay, let's dive right into this explainer on infrastructure coordination patterns. Now, if you caught our previous lesson, Component Integration Overview, you already know the basics of how different pieces of a distributed system actually talk to each other. But today, we're going to figure out how we prevent thousands of inbound transactions from turning our carefully designed system into total unmanageable chaos. I mean, when you have load balancers, sequencers, validators, and storage services all operating at completely different speeds, how do you make sure they don't just step all over each other's toes? Well, that's exactly what we're solving today.
Here's our blueprint for today. We'll be covering 1. Coordination chaos, 2. System harmony goals, 3. The pattern toolbox, 4. The integration pipeline, and finally, 5. Trade-offs and choices. Let's get into it.
Section 1. Welcome to Coordination Chaos. Let's set the stage.
So I want you to imagine a high-tech postal sorting facility. You've got thousands of packages arriving simultaneously from hundreds of different delivery trucks. Without a highly engineered, strictly enforced sorting system, it is just pure, unadulterated chaos. Packages get lost, some get processed twice, and the poor workers at the end of the line are, frankly, completely overwhelmed. Well, in a Web3 architecture, those packages are user transactions. And coordination patterns, those are the ingenious machines on our assembly line that fix this whole mess. They dictate exactly how different parts of your system agree on timing, order, and message handling, basically preventing systemic failure.
Section 2. 4 goals of system harmony. The absolute constraints we have to work with.
To design our facility correctly, every coordination pattern has to balance 4 specific pillars. First up, ordering, ensuring a stable, predictable sequence for dependent events. Second is durability, which is making absolutely sure we prevent data loss even if a node literally catches fire. Third, liveness, guaranteeing the system keeps making progress despite partial failures. And fourth, flow control, which manages mismatches in throughput so fast producers don't just crush slower consumers. Honestly, without these 4 pillars, and I really cannot stress flow control enough here, your network gateway is basically just a guy trying to drink from a fire hose while juggling chainsaws. It might look cool for a split second, but it's definitely going to end in disaster.
Section 3. The infrastructure pattern toolbox. Let's look at our core tools. All right, our first tool is the centralized sequencer. Think of this as the single, all-powerful boss of the master sorting conveyor belt. Every single message that enters the system goes straight to this one authority, and it gets stamped with a strict position. The massive advantage here: predictable, incredibly low latency decision-making. Ordering becomes absolutely trivial. But you guessed it, the catch is that this boss is a single point of failure. If the centralized sequencer goes down, the whole line just stops, unless you've heavily engineered a backup failover system. Now, on the flip side, we have gossip and deterministic anchors. This is the complete opposite of the single boss model. Here, all the workers on the floor rapidly compare notes with each other. This is what we call epidemic peer-to-peer message propagation. But wait, without a boss, how do they actually agree on the order? Well, they rely on an unbreakable cryptographic atomic clock, like Solana's proof of history, or POH. They basically use these POH timestamps as deterministic anchors to break any ties. It scales horizontally beautifully, but figuring out the final order requires some pretty complex reconciliation rules when nodes temporarily disagree. As we often discuss in our Forge College architecture programs, choosing between these two fundamentally shapes your entire network. You're basically deciding, does your system prioritize immediate, absolute order, which that sequencer gives you, or partition-tolerant, high availability, which you get from gossip and anchors? If you need strict ordering for simple clients, you go centralized. But if you have a massive global cluster where availability is absolute king, gossip with deterministic anchors is for sure your best friend.
Okay, moving along, next up in our toolbox is acknowledgement and commit. This pattern actually moves the complexity directly into the communication protocol. It guarantees that a package isn't considered delivered until we get an ironclad, explicitly signed receipt from the downstream component. This heavily increases our durability pillar, right? Because we know exactly what data is safe. But, and it's a big but, waiting for those receipts to go back and forth can add some serious end-to-end latency to the user experience.
So, to amortize that exact latency we just talked about, we use batching and checkpointing. Instead of asking for a receipt for every single little envelope, we effectively shrink wrap an entire massive pallet of packages all at once. The components agree on a periodic cut point, which is often aligned seamlessly to those pole hock ticks we mentioned earlier, and they flish the state all at the same time. This way, if something fails catastrophically, we don't have to start from scratch. We only have to replay the data from our last saved durable cut point. It makes storage incredibly efficient.
Finally, we have backpressure and flow control. This acts as the vital traffic lights holding delivery trucks back from the loading dock. Systems use mechanisms like token buckets and bounded queues to literally push back against inbound traffic when they are overwhelmed. It prevents fast producers, like, say, millions of users suddenly clicking buy at the same time, from cascading a systemic failure across the entire cluster. It basically ensures your system gracefully degrades by saying, "Whoa, hold on a second," rather than just crashing completely.
Section 4, Real-World Integration Pipeline. Let's see how this actually comes together.
You know, it's pretty rare that you'd use just one of these patterns. It's all about layering them. Let's trace a transaction's journey through a hybrid pipeline. Step 1. At request ingress, we immediately apply flow control at the gateway so we don't get flooded. Step 2. We pass it to the sequencer to assign an absolute order, anchoring it to a POH tick. Step 3. During validator processing, we wait for those durable acknowledgements, those ironclad receipts, so we know it's safe. Step 4, we batch those writes to archival storage using checkpointing to save on processing overhead. And finally, Step 5, we lean on our POH offsets for failure recovery. So if a node suddenly dies, we know exactly where in time to resume when the leader rotates.
Section 5. Trade-offs and practical choices. It's time to weigh our options.
Look, engineering is fundamentally about trade-offs. A centralized sequencer gives you low decision latency, but you risk a single point of failure. Gossip gives you wide availability, but you deal with transient divergence. ACKs provide strong durability, but they increase latency unless you combine them with batching, which, amortizes that cost but increases your replay window. And flow control? It prevents overload, but it can cause systemic throttling if you misconfigure the thresholds. The really key takeaway here is that hybrid architectures, like combining a lightning-fast front-end sequencer with gossiped processing across the back-end nodes, often yield the absolute best, most resilient, practical results. Which brings us to the ultimate question for our next lesson. How must storage semantics actually adapt to these exact coordination patterns without undermining the latency we just worked so hard to optimize? We are going to tackle that head-on in our upcoming explainer, Data Storage Enhancement Strategies, which is part of our broader look at proof of history, Solana's timekeeping solution, right here in the Advanced Solana Concepts track. Leave your previous assumptions at the door, guys, because the way Web3 storage interacts with proof of history is truly mind-bending. Be sure to visit forge.college to dive deeper into this topic and continue exploring this incredibly vital Web3 architecture. Thanks so much for joining me on this explainer, and I'll catch you in the next one.